Okay, good afternoon, students. So we are back for the fourth session of Chemistry Olympiad training, and today we will be talking about ideal gases and the gas laws. So what is an ideal gas? Why focus on the gaseous state specifically? So let's take a closer look today at what the gaseous state looks like. What are some assumptions that we make about an ideal gas? As the name suggests, ideal gases are not real. They do not represent real gases 100% accurately. There are some assumptions that we make about ideal gases that real gases do not really obey 100%, but ideal gases just provide a very simple, a very basic starting point for us to understand, okay, how particles are. So as you can see the learning outcomes, these are the learning outcomes which you will learn again if you do more chemistry later on. But the first learning outcome really is to understand what the assumptions of ideal gases are. There are 5 assumptions, all right? And secondly, we need to understand what we mean by energy present in particles, energy present in chemicals. So this is actually from pure physics. So if you offer pure physics as a subject, you would be learning about this. Or if you're in Sec 4, you would already have learned this in your pure physics class. Okay? And finally, we will learn about the ideal gas equation, which I'll explain more later what that is. And from the equation, we can manipulate the equation, move the terms around, and we can start drawing different types of graphs. Okay? And why are we focusing on this chapter? We are focusing on this chapter, number 1, because Chemistry Olympiad in previous years, they have tested the graphs. Okay? So to draw the graphs, you need to first know the ideal gas equation. Number 2, I think this is also a useful midpoint check for us. Okay, so if you think about it in Sec 3 chemistry, you have been learning a few things. You have learned particles, right? Kinetic particle theory. So you learn that things are made of particles. You have learned that particles are arranged differently in the solid, liquid, gaseous states. Okay, then you went on to talk about atoms. So atoms are the most basic particles that make up all chemical substances. Then you learn what's inside an atom. You learn how atoms can bond together. That's bonding, ionic bonding, covalent bonding, as well as metallic bonding. All right, so this is where we have left off so far for Sec 3 chemistry. Okay, for my Sec 4 students, yes, this is what we did in Sec 3 as well. But now, it is also apt to talk about ideal gas because we are learning about energy. So in Sec 4, we learn about energy change of a reaction. We learn about energy level diagram. So what does it mean to say that, oh, this thing has this much energy? What does it actually mean? So today we are going to examine what is internal energy of a chemical substance. When we say that, oh, water has this amount of energy, what do we actually mean? Next, we're going to focus on the gaseous state and talk about what is an ideal gas and what are the basic assumptions that you make about an ideal gas. Finally, we will end off today by talking about the ideal gas equation and the graphs derived from the ideal gas equation. Okay, so let's look at the first page first. I hope you realize that the ideal gas is a model. It is not reality. It's just a model. So in chemistry or science in general, we always try to understand how come things happen the way they are. We can do this through measurements, experiments, making observations using our 5 senses, predictions, gathering evidence and data, and finally, conclusions. But you must think, it is not always possible to witness everything using your 5 senses, especially in chemistry. If you talk about particles, it's not possible to see particles on a daily basis. You can't see particles. They are too small to be seen, right? And there are many situations in which there are simply too many factors to consider, right? There may be more than one type of bonding. There could be more than one type of atom. There could be more than one size of atom, all right? Too many different factors that may affect our understanding of the particles. So in such cases, we really need models to simplify the situation to help us visualize a situation better. And that's why we use models in chemistry as well as in science. So ideal gas is a model. Okay, the atomic structure model is another model if you think about it. You can't see atoms with your eyes, but we can use models to represent atoms. All right, so this is where we will begin today. So before we go to ideal gas, let's try to understand what we mean by energy. Okay, so what do we actually mean by internal energy of a substance? So since primary school, you probably learned the word chemical energy. So what is chemical energy? There is chemical potential energy stored in food, in fuels. This is how you obtain energy through food. Food is digested. The energy that's stored in food is released as energy for your cell's activities, right? Similarly, when you burn petrol, you burn diesel, that releases energy to power the car. So this is the idea of chemical potential energy. And in kinetic particle theory, for the Sec 3s, you just learned this. You are introduced to the fact that particles are in constant random motion. This means that they are constantly moving, and that means that particles have kinetic energy. So if you were to put these two together, chemical potential, kinetic energy of particles together, we can arrive at what we call the internal energy of a substance. So every single chemical substance must have the internal energy, and the internal energy is equals to two different terms added together. First, we have the microscopic potential energy of particles. Second, we have the microscopic kinetic energy of particles. Okay, so let's look deeper at each term. The internal potential energy or microscopic potential energy, it is due to the forces of attraction between particles. So you have learned there are forces of attraction between particles. That is why you have potential energy between particles. Okay. Now, importantly, you need to realize the stronger the forces of attraction between particles, the lower the potential energy. Stronger attractive forces, lower the potential energy. Why? Why is it that when the forces are stronger, you lower the energy? That's because when the forces of attraction are stronger, the substance is more stable. More stable substances have lower energies. They have less energy to react. That's why they are more stable. So take for example, okay? Take for example, after the hydrogen atoms come together to form the H2 molecule, the H2 molecule is more stable, so it has a lower energy than the hydrogen atoms themselves. So we say that H2 has a lower internal or microscopic potential energy than hydrogen atoms separated. Okay? For the Sec 4s, hopefully this makes more sense now that you have learned energy level diagrams, right? So whenever you have an energy level diagram and the energy decreases, what it means now is that you are forming more stable products. So if you recall the energy level diagram that we drew in class, reactants, products. If the energy of the products is lower than the reactants, it means that the products are more stable compared to the reactants. Okay, so that's what it means. And why are the products more stable? Because you have formed more stronger bonds. Stronger forces of attraction are formed. Therefore, the energy is lower because the stronger the forces of attraction, the lower the microscopic potential energy. Okay, so hopefully for my Sec 4s, now you can start to connect the dots together, connect this with what you have learned in energy changes. Okay, so that's microscopic potential energy. So now we look at kinetic energy. So what is kinetic energy? Kinetic energy is obviously due to the movement of particles. Kinetic movement of particles. So what is this affected by? So this is affected by temperature. Okay, so now if you think back to kinetic particle theory, you have learned if I increase the temperature, the particles will gain kinetic energy and move faster. So the higher the temperature, the faster particles will move. As a result of that, the higher the kinetic energy of particles. Okay? So we also say commonly in physics that temperature is directly proportional to the average kinetic energy of particles. Okay, this is what your physics teacher will tell you later on. Temperature is a measure of the average kinetic energy of particles. Okay. So together, the potential energy, which is related to the forces of attraction, the kinetic energy, which is related to temperature, taken together, this tells us the internal energy present in any chemical substance. Okay. So this table nicely summarizes the two types of energies that particles can have and will have. So of course, does a glass of water sitting on the table have any energy? The answer is of course, yes. Water is a chemical, right? Even though if you look at the water, you don't see any energy, but the particles, the molecules of water have energy. They have microscopic kinetic energy because the molecules are constantly moving around. They also have the microscopic potential energy because they are attractive forces between the water molecules. They are attractive forces between the atoms in water. Okay? So how important is this internal energy? It is important in allowing us to predict the reactivity of chemicals. So again, you go back to lower sec science or physics as well. Energy is the ability, the capacity to do work. You have learned that since lower sec science. Energy is the ability to do work. So if you were to perceive, you were to view a chemical reaction as a form of chemical work, chemical reactions are chemical work, right? Having higher energy, higher internal energy means higher capacity to undergo reactions. Therefore, a higher energy means a substance is likely to be more reactive. And that's an important concept. Okay, higher energy, more reactive. I hope you remember this. It's an important concept. Okay, so now let's move on. Now we have understood the energy present in a chemical substance. We now know that chemical substances have energy. We now know that chemical substances also have different states of matter. There's solids, liquids, and gases. We are just going to zoom into one state, which is gas. Why? So I've written there, right? You might wonder, why look at gases of all the three states of matter? Well, number one, many common substances around you exist as gases. So good examples, O2, oxygen, N2, nitrogen, carbon dioxide, CO2, all right? Now, the second reason, which is the more important reason, is that you can make certain assumptions about the movement, forces of attraction, and properties of gases, and that's important, okay? So I hope you realize that the reason why you have ideal gases and you look at gases is because you want to make assumptions. And these assumptions are easier to make for gases because gases, the particles are far apart. Gases, the particles are moving about at high speeds. Okay? So let's look at the assumptions of an ideal gas. I hope you realize ideal means not real. Not real. Okay? So in reality, gases don't exactly follow this, but let's use this as a starting point. Now, there are 5 underlying assumptions of the ideal gas model. So let me read them out to you. You also have it on your notes. The first assumption, an ideal gas consists of small particles of negligible volume. Okay, so the particles don't have volume. The volume of particles is 0. The particles are widely separated and are free to move anywhere in the container they are in. So immediately you start thinking, is this really true? Does carbon dioxide gas really not have any volume? A molecule of CO2 surely has volume, right? So is it small enough to be negligible? So that's the first question. Okay, so gets you thinking, do you think all gases will follow these assumptions? The second assumption, there are no forces of attraction between particles in an ideal gas. Immediately, This sounds wrong, right? You have learned in bonding. Your teachers probably taught you there must be some forces of attraction between particles, even in a gas, right? However, in a gas, the forces of attraction between the particles in a gas are weaker, but it doesn't mean there are no forces. So this is an assumption that we make about ideal gases, and you can begin to see why ideal gases and real gases will not be exactly the same. Because in a real gas, there will be some weak forces of attraction between particles. Thirdly, third assumption, the gas particles are in constant random motion and will collide with each other and with the walls of the container. Okay? The fourth assumption, the collisions between particles in an ideal gas are perfectly elastic. Now, this word you have not learned. You will learn it at A-level physics. Perfectly elastic collisions are collisions where there is no loss of kinetic energy during and after the collision. All right? So kinetic energy is conserved. Finally, the fifth assumption, which is not really an assumption, is actually a definition. The average kinetic energy of particles is in a gas is directly proportional to its temperature. That is more like a definition. Okay, so I've written down there think. Look at the 5 assumptions that are numbered above, 1, 2, 3, 4, 5. Then think back towards what you have learned. Which assumptions do you think will not be followed by a real gas? So I'm sure there are certain assumptions here that are probably not very correct for a real gas. So which ones do you think will not be followed? Can you type in the chat? Number 1, 2, 3, 4, or 5. Which ones do you think will not be followed by a real gas? Okay, some of you type 1, some of you type 4. Okay. That's it. No one else is typing. 2. Okay. Well, the answer, of course, is a number of them are not followed by real gases. Okay. So the first one that's not followed by real gas is assumption 1. Obviously, particles cannot have negligible volume. Particles have volume, right? That's obvious. They are made of atoms, they are made of molecules, which are made of atoms ultimately. All these have volume, they have a certain size to them, right? They take up certain space. But of course, if I were to compare larger molecules have more significant volumes. That's obvious, right? Some molecules are bigger, therefore their volumes are more significant. So take, for example, CO2. CO2 is considered a larger molecule for obvious reasons because there's 1 carbon and 2 oxygen. Each carbon, each oxygen already is larger, and if you put them together in a CO2 molecule, it means the CO2 molecule is larger. Now, there are other molecules that are probably also quite large, and they are gases. Take, for example, SO2. Sulfur dioxide is a gas. Sulfur dioxide obviously is also a larger molecule. Okay, there are more examples, but let's just use these 2 examples, okay? So we can already predict SO2, CO2 probably will not follow the ideal gas model very, very well because their molecules are pretty large, they will have significant volumes. The next assumption that most gases will not follow is, of course, assumption number 2. There are no forces of attraction between particles. Obviously, that's not very true. In real gases, there are weak intermolecular forces of attraction. Okay, so for those who have learned the covalent bonding, you would have learned that in a simple molecular structure, there are weak intermolecular forces of attraction between the molecules. So it is incorrect to say that there are no forces of attraction. Clearly, that's an assumption that is not real. In a real gas, there must be the weak intermolecular forces of attraction. Okay? And this is not negligible. The weak intermolecular forces of attraction can be significant. These are usually more significant in gases like ammonia. Okay, ammonia doesn't really follow the ideal gas model because in ammonia, the intermolecular forces of attraction are quite significant. Okay, ammonia is a good example. Okay, so assumption 1, assumption 2 probably will not be followed by real gases. So just take note. Okay, so these are the 2 assumptions that probably will not be followed. Assumption 4 as well. Okay, it is probably not true that collisions are always perfectly elastic. Okay, sometimes when particles collide, they actually release energy in other forms, okay, like heat. Okay, so it may not always be true that kinetic energy, there's no loss of kinetic energy during or after the collision. Okay, so now let's take a look. Assumption 1, assumption 2. Assumption 1 is about volume. Assumption 2 is about forces of attraction, right? So, given these 2 assumptions are not followed, which gases will be most ideal? The most ideal gases will be the gases where the molecules are very small, right? Like what? The smallest possible molecule is probably hydrogen gas. H2 consists of 2 hydrogen atoms. Each hydrogen is very small. Okay. Helium, noble gas. Okay, these are very, very small molecules and atoms. Next, very weak intermolecular forces of attraction. Again, hydrogen and helium. These are the ones with very weak intermolecular forces of attraction. Okay. So these are probably your most ideal, the gases that are closest to ideal behavior. Okay, next, if you know that, okay, volume can be significant, forces of attraction can be significant, what can you do? Gases are also most ideal at low pressure. Low pressure. Okay, gases are most ideal at low pressure. Why? Why is it that at low pressure they are most ideal? This is because at low pressure, the volume of the container is large. When the container is so big, what it means is that each individual molecule's volume is less significant as a percentage of the total volume of the container. Big container, but the molecule not so significant anymore. Okay? Next, at low pressure is most ideal. Besides that, when the temperature is high, gases are also more ideal. Okay? Why? Because when the temperature is high, your particles are moving around at high speed. If they are moving around at high speed, that means they are less likely to come closer together. They are less likely to come closer together to form stronger forces of attraction. When particles are moving around at high speed, the forces of attraction are weaker between them. Okay? Can? So low pressure, high temperature is most ideal. Okay? So that's the 5 assumptions of ideal gases. Have this awareness that, okay, maybe not all the assumptions are valid. And finally, gases may be most ideal when the pressure is low, temperature is high. Okay? So moving on to the next page, we mentioned all these terms, right? Temperature, volume, pressure. So what can you actually measure in the lab? So I'm sure you are familiar. You can measure temperature in the lab. You measure that using a thermometer. But importantly, the unit for temperature, the SI unit for temperature is actually Kelvin. It's not degrees Celsius. You actually learned this in lower sec. So today you will need to use kelvins a lot. Please take note, kelvins are not the same as degrees Celsius. The temperature in Kelvin is equals to the temperature in degrees Celsius plus 273. Okay? Next, volume. I hope you know by now, volume, gases basically take the volume of the container they are in. And the unit is usually meters cube, dm cube. It's also common in chemistry. All right. So this is the conversion between meters cube and dm cube. If I want to go from dm cube to meter cube, dm cube, you want to go to meter cube, you divide by 1000. Okay. And vice versa, meter cube to dm cube, you times 1000. All right. So this is the conversion between the two units. Next, pressure. Now, pressure of a gas can be measured using what we call a manometer. There are two units for pressure, pascals or atmospheres. So the conversion is 1 atmosphere is equals to 101,325 pascals. Okay, don't stress yourself out over memorizing this. Just have the awareness that there are two different units for pressure. Now, more importantly, you need to know, why do gases even have pressure? All right. So if you recall to Sec 2, you learn pressure. Pressure is equals to force over area. So what force is there from a gas? Well, gas particles collide with the walls of the container. As a result of that, when they collide, they exert a force on the walls of the container. Therefore, the more frequent and more forceful the collisions are, the higher the pressure of a gas. Okay? So pressure of a gas is due to the particles of gas colliding with the walls of the container. All right, which is illustrated in the picture in your notes. Okay, finally, we have the amount of gas. Now, amount of gas, right? Amount in chemistry is measured in moles. Okay, so for the Sec 3 students, you'll be doing mole concept later on. Okay, so amount of a gas is measured in moles. Now, you cannot measure the amount directly. What you usually do is you measure mass of a gas, then you divide by the relative molecular mass of the gas. So mass over mR is equals to amount. Again, don't be overly worried about this for now. Just be introduced to the fact that amount in chemistry is measured in moles. Okay. So with that, we move on to the ideal gas equation, which is PV is equals to nRT. What? So what does P stand for? What does V stand for? What does N stand for? So let's go through one by one. P is pressure. Pressure of the gas. V, volume of the gas, which is the volume of the container it's in. Okay. Can? So take note, volume of gas is the volume of the container, basically. N. Now, N in chemistry is the number of moles of the gas. Okay. R is interesting. R is what we call the molar gas constant. As the name suggests, it's constant, meaning it's just a value. Finally, T. Now, T is the most important one today. T is temperature. But today's temperature must be in kelvins. To use the ideal gas equation, you must work in kelvins. It wouldn't work if it's in degrees Celsius. And that's why, as part of physics, we always teach you kelvins. You need to use kelvins in your equations. Okay, so today, we're going to use this equation quite a lot. But you need to know that this equation, to use it, you must use the units correctly. The units come in two sets. Set number 1, set number 2. These are set combinations to use. What do I mean? If I want to use pascals for pressure, I must make sure my unit for volume is meter cube. And if I have pascals, meter cube, I must use R is 8.31. It's one set, Pascals, meter cube, 8.31. On the other hand, if I wanted to use atmospheres for my pressure, my unit for volume must be dm cube. And my value of R will be 0.082. So you must ensure you use the right combination of units and R. Okay? So now we're going to do a little bit of math. So using the ideal gas equation, prove that 1 mole of an ideal gas occupies a volume of 24 dm cube at a temperature of 298 Kelvin and 1 atmosphere. So you always highlight chemical names and numbers. 1 mole, number. 24 dm cube, number. Temperature is 298 Kelvin. Pressure is 1 atmospheres. Always highlight the numbers because they tell you what to do next. You realize that, hey, it's in atmospheres. This means that you must choose set number 2. Atmosphere dm cube 0.082. So I must prove that volume is 24. How do I do that? I find the volume. Volume is V. I make V the subject of the formula. How to make that the subject of formula? V is equals to nRT over P. N is number of mole. Number of mole is 1. This is N. 1 mole is N. Right? R is 0.082 because I am using pressure in atmospheres. So 0.082. Temperature, T, is 298. So 1 times R is 0.082 times 298. So this is nRT. Finally, divide by P. P is 1 atmosphere. So this is P. So if you do it, and you round it off to the nearest whole number, V is 24 dm cube. And I hope my Sec 4 students finally realize this is mole concept, right? I taught you all last year, 1 mole of a gas occupies a volume of 24 dm cube at room temperature and pressure. This is how you prove it. You use the ideal gas equation, you rearrange to find volume, you sub in room temperature 298 Kelvin, you sub in 1 atmosphere depth pressure, and that gives you 24 dm cube to the nearest whole number. Okay, and that's why we can use the formula triangle later on in mole concept, right? Vn24. Okay, for the Sec 3 students, you'll be doing this very shortly in mole concept. Okay, so just know that using the ideal gas equation by subbing in the correct numbers with the correct units, you can actually find different quantities. Okay, now with that, we come to checkpoint number 1. Okay, which I'm going to give you a few minutes to work on. Okay, the answers are all given. So can I trust you to work on checkpoint number 1 now? Let's take about 10 minutes to work on at least question 1A all the way to 1E. Okay, let's work on 1A to 1E. The trick here is to take note that N is 1. 1 mole of ideal gas means N is equals to 1. Okay, that's the first important thing to take note. Next important thing to take note, the units of volume and pressure will allow you to choose the correct value of R. What do I mean? Just now I told you, right, set number 1, set number 2. You must use the correct set of units. You must use the correct R for that set. Okay, so it's either 8.31 or 0.082. So please, let's work on this now, 1A to 1E. Okay, I'll give you 10 minutes until 5:50 to work on this. If you have any problems, please type in the chat so that I can help you. All right. So please start doing it now. Okay, you should be working on it. So 2 minutes has passed. You should be on 1A and finishing it and check your answers, all right? So it's important to ensure that you use the correct units with the correct R. So if you look at 1A, right, pressure is 1 atmospheres. Atmosphere means immediately you set number 2. Your volume is in dm cube. Your R is 0.082 for 1A. Okay, so now think about 1B. 1B, your volume is in dm cube. So again, dm cube for volume belongs to set number 2. So your pressure is in atmospheres, your R is 0.082. All right, so please make sure that you use the correct units, correct R. Okay, so again, if you have any questions, please unmute yourself to ask. If not, type in the chat so that I can help you. Okay, I'm giving you all 4 more minutes to finish 1A to 1E. Just check that you know how to use the equation. So for those of you in the Zoom room, I hope you are doing it. Later on, I will just ask you to give me a thumbs up to show that whether you can do it or not. Okay, the best way to do this really is to practice. Okay, so just practice moving the equation around to find either temperature, pressure, or volume. You must be familiar with how to move the equation around because later on we're going to be drawing some graphs. To do it, you need to be familiar with the equation. Okay. Okay, maybe just about 1 more minute to finish up what you're doing and make sure you check your answers against the numerical answers provided so that you know whether you're on the right track or not. Okay, it's 5:50. All right. Can everyone just give me a thumbs up if you have tried at least 1 or 2 of the problems and you managed to get the answer? Okay. Okay, thanks. Jet, Wenhui, Jinghang. All right, Sumaya as well. Okay, Kyla, great. Okay, Alyssa. Okay, Audrey, I presume. Okay, Jamin, thank you. All right, so the important thing is to try it, okay? I know it's just an equation, just subbing in numbers, okay? The important thing is always to get the units right, to choose the R correctly. So this is actually A-level chemistry, I'll be honest, okay? And many of you, actually, you may consider doing A-level chemistry in future. One of the problems that my A-level students had in the past was, whenever they come to ideal gas, they always forget that the units must go in a certain combination. The R must be chosen correctly. So once you can get that correct, right, you will do better at A-level chemistry for this chapter. Now let's do question 2 together though. Let's read question 2 together. So I always tell my students, always highlight the numbers. The numbers tell you something important, so do the chemical names. All right, so you know that the balloon is 1 dm cube. It contains 0.04 moles of helium gas. So those are numbers that you want to highlight. Chemical name as well, helium gas. So as mentioned just now, helium is a very small atom. It's also likely to be more ideal. And indeed, helium follows ideal gas behavior quite closely. Now, it's released at sea level and rises to reach a height where the pressure is 0.9 atmospheres and the temperature is 10 degrees Celsius. Calculate the volume at this new height. This means the volume is not 1 dm cube anymore. You are finding V. And you know that based on the ideal gas equation, PV is equals to nRT. So V is equals to nRT over P. Okay? So now you want to find V. V is equals to nRT over P. And this is where you must be very, very careful. What is N? N is number of moles. So look for moles. Moles, 0.04. So N is 0.04. P is 0.9. Atmosphere, important. So atmosphere is a big clue to you already. This means that the units follow set number 2. Atmospheres, dm cube, and the R is 0.082. So now let's try to sub in. N is 0.04. R is 0.082. The next challenge is T. If you follow what I said just now, temperature, the unit has to be kelvins. All right. If it's not kelvins, you can't sub in. So you cannot sub in 10 because 10 is degrees Celsius. You must first convert 10 degrees Celsius to kelvins. The way to convert is to take 10 plus 273. Which means it's 283 kelvins. So you sub in 283 as the temperature, divide by the pressure of 0.9. If you do that with a calculator, you'll be able to calculate that as 1.03 dm cube. 3 significant figures. Okay, so what do you notice? At sea level, right, the balloon has a volume of 1 dm cube. If it were to rise, actually it expands to 1.03 dm cube. Okay, it expands because the volume actually increased to 1.03. And the reason why it expanded is because the pressure is now 0.9 atmospheres. The pressure is now lower, therefore the volume is larger. Okay, Ken? So that was question number 2. I just want to quickly demonstrate how the units are important, how the units guide you in the selection of what value of R to use. Okay, and take note, if the unit is degrees Celsius, cannot, you must convert degrees Celsius to Kelvins. Okay, so I would like you to try the remainder of question 1 if you have not finished. I would like you to try question number 3 as well later on when you have time. Okay, the numerical answers are provided for all these questions, so please check the numerical answers. Now let's use the ideal gas equation and draw some graphs. What do I mean by drawing graphs? Well, let's look. What if Mr. So wanted you to draw the volume temperature graph? The graph of volume against temperature. So whenever we say volume temperature graph, the first variable is the y-axis. The first thing we say is the y-axis. So the y-axis is volume in this case. So what do? If we know that volume is y-axis, we will make volume the subject of the formula. So we rearrange the ideal gas equation. PV equals nRT. So what is V? V is equals to nRT over P. Okay. Next, what do? We know that it's volume temperature graph at constant pressure. Whenever you do this, right, there's always bound to be something that is kept constant. So take note, constant pressure. Now, constant means same, right? So same means iso. Iso means same. Same pressure means isobaric. Baric means pressure. Okay, so you must make sense of the word. Isobaric means same pressure, constant pressure. Okay, can? That's why the pure physics students, if you are on the topic of pressure, you may have heard of this word called hyperbaric. Hyperbaric means high pressure. Okay, barometer, B-A-R-O, barometer is also an instrument to measure pressure. So whenever we read this word baric or baro means pressure. Okay, now, so what's the idea of knowing that pressure is constant? If pressure is constant means P is constant, right? Besides that, R is constant. R is a constant number. N is also constant because it's a fixed amount of ideal gas. So N is constant, R is constant, P is constant. So N, R, P, they're all constants. You group constants together. That's algebra. Group like terms together. Constant, put one side. Okay? So NR over P, the green ones, NR over P are constants. So T is the variable. Okay? So I will rewrite my equation that way. I will usually group my constant together. I'll put the variable as a separate term. So NR over P, bracket T. So what's the purpose of doing this? Because you must sketch graph, right? Sketch graph means you must know what's the y-axis, what's the x-axis. So in this case, V is the y, T is the x. So what have you ended up with? You have basically ended up with y is equals to constant times x. Y is equals to mx. Y equals to mx, needless to say, is a familiar sounding graph to you, right? You have learned this in Sec 2, maybe term 2. Sec 2, term 2, you learn how to draw a straight line graph. You learn that the equation of a straight line is y equals to mx plus c. So isn't it the same in this case? Volume against temperature is a straight line graph, and the gradient is nR over P. And not only that, you know that the intercept is the origin, right? Y equals to mx plus c. In this case, the c is 0. You don't even see it. And hence, the volume temperature graph is a straight line graph that passes through the origin and has gradient nR over P. And indeed, that's the case. If you plot volume against temperature in kelvins, you will get a straight line graph that passes through the origin. And the gradient of this straight line graph is equals to nR over P. Then now let's think common sense. If I were to heat up something to a higher temperature, what happens to the volume? So you learned that since primary school, right? When things are heated, they expand in volume. Doesn't it make sense now? Volume increases as temperature increases. And now you have proven it using the ideal gas equation. And this law that volume is proportional to temperature at constant pressure, this is called Charles' law. Okay, Charles' law states that volume is proportional to temperature at constant pressure. So the physics students, you would have learned the gas laws. This is one of the 3 gas laws. Charles' law states that volume of a gas is proportional to temperature. Again, this comes from the ideal gas equation, PV equals to nRT. Okay, the straight line graph tells you that it's directly proportional. Okay, so now from the volume temperature graph, we move on to the pressure temperature graph. This time round, pressure is the y-axis because it comes first. Pressure against temperature. So pressure is the y, temperature is the x. And you realize there's again something at constant volume. You already start to see the pattern, right? PV equals to nRT. If P and T are the variables, that means V is the constant. Okay? There must only be 2 variables and the rest must be constant. So constant volume, it's isovolumetric. Iso means same, volumetric means volume. Same volume. Another word for isovolumetric is isochoric. All right? So we do the same. PV equals to nRT. You start from there first. Then P is your y-axis. So you make P the subject of formula. So P is equals to nRT over V. Right? Again, we know volume is constant. So volume is constant. So nR over V are constants. So P, sorry, oh, I made a mistake. P is equals to nR over V times T. Okay, so please correct this error here. I'm so sorry about this error. So P is equals to nR over V times T. So again, you realize, oh, T is the y-axis, T is the x-axis. So again, we end up with y equals to mx, which is a straight line graph through the origin. So the pressure temperature graph at constant volume, sorry, I made a mistake here. The pressure temperature graph at constant volume is a straight line graph that passes through the origin and the gradient is nR over V. Okay? So again, indeed, as you plot the graph, you realize that pressure against temperature is a straight line graph that passes through the origin. The gradient is nR over V. Okay, so please correct the 2 typo errors. I'm really sorry about the typo errors. Okay, just to correct the 2 start typo errors before we move on. All right. So once you have corrected the typo errors and you have understood the shape of the graph, can you please give me a thumbs up so that I know I can move on from here? Okay, thank you. Okay, so we can see it's a straight line graph, straight line graph, and it passes through the origin because in this case, it's just y equals to mx. There's no intercept. The intercept is 0. So straight line graph always means directly proportional. So pressure is directly proportional to temperature at constant volume. This is called the pressure law. This is the second gas law that you will learn in pure physics, right? Pressure is proportional to temperature under constant volume. So we move on to the next one. Is the volume of pressure against, is the graph of pressure against volume at constant temperature. Constant temperature, isothermal. Thermal in this case refers to temperature. Okay, so we have gone through isobaric. Isobaric is constant pressure. Isochoric, volumetric, that's constant volume. Isothermal is the constant temperature. So again, we do the same. Pressure is the y-axis, so make P the subject of the formula. So PV equals nRT, P is equals to nRT over V. But this time around, T is constant, so nRT are constants. Then what do you see? nRT times 1 over V. So what graph do you end up with now? Is it still straight line? If you plot, okay, I made a careless mistake again. It's P is equals to nRT times 1 over V. So what do you realize? All right. Is it still a straight line graph? If you look at it, volume is in the denominator, it's 1 over V, meaning now you have 1 over X. So what is this graph like? This is a Y is equals to 1 over X graph. It's no longer a straight line. Just now it was a straight line because it's Y equals to MX, right? But this is not. This is 1 over X. So what does 1 over X look like? So the Sec 3s, you may just have learned this. This is the shape of the graph of Y equals to 1 over X. So in this case, pressure is proportional to 1 over V. Okay, so please correct a typo error. Again, there's a typo error, a second typo error here. I'm really sorry. It's constant temperature. Okay, so to correct these 2 typo errors, the shape of the graph is a reciprocal graph, so it's 1 over X. Okay, so this is the shape of the graph. Now, for the Sec 4 students, you may realize that Y equals to 1 over X actually looks like this. Right? There are actually 2 sides to the graph. So some of you may be wondering, how come the Y equals 1 over X doesn't have this negative portion? Right? Why doesn't it have the negative portion? Remember, we are plotting pressure against volume. Can pressure be negative? Can volume be negative? No, right? So this is inadmissible, not applicable, right? What you call inadmissible, reject this portion. Because pressure and volume cannot be negative. That's why we only have the positive side of the graph. Okay, for the Sec 4 AMAT students, you would have done this graph in AMATs as well. For the Sec 3 students, you should be doing this graph soon under the topic of exponential, logarithmic, and power functions. All right. So please correct the 2 start typo errors again. I'm so sorry about typo errors. Okay. So what you realize now is that pressure is proportional to 1 over volume. Pressure is proportional to 1 over volume. If you think back to Sec 2 when you first learned direct and inverse proportion, 1 over something means inverse proportion. So pressure is inversely proportional to volume. This is called Boyle's law. Okay? Boyle's law. Okay? Now, the pure physics students must be asking, but Boyle's law doesn't even look like this, right? We learn Boyle's law in a different form. We learn Boyle's law as P1V1 equals to P2V2, right? That's Boyle's law that you have learned. So now a quick mathematical calculation will get me to this. If I move the V on one side and P on one side, don't you realize the P1 and the V1, one is on top, one is below? Similarly, the P2 and the V2, one is on top, one is below. This immediately tells you that pressure and volume are inversely proportional to each other. One is in the numerator, the other one must be in the denominator, and vice versa. Okay, so that's Boyle's law. That's how we arrive at P1V1 equals to P2V2 for Boyle's law, which I'm sure the pure physics students probably used to solve many problems last year under thermal physics. Okay, finally, move on to the last graph. The last graph looks very strange. Plot PV over RT against P. Never mind, strange also never mind. We start with PV equals nRT. Remember, we always make the y-axis the subject of the formula. So let's make the y-axis the subject of formula. PV over RT is the subject. So PV over RT equals to N, number of moles. But N is a constant number because it's a fixed amount of ideal gas, right? Meaning N is constant. So how do you plot this? You plot this by, okay, drawing a horizontal straight line. It's like y equals to 3. How do you draw the graph? Just draw the straight line, a horizontal straight line. Okay, so this is PV over RT against P. This is a straight line. All right. So the idea behind all this is always rearrange the ideal gas equation. Then you think through what is constant. What is constant, you put together. What's the y-axis? What's the x-axis? Okay, be mindful of that. All right, and finally, checkpoint number 2. This is the actual ChemO question. Which of the following pressure volume diagram depicts an isochoric process? So we just learned this. Isochoric means constant volume. All right, isochoric means constant volume. Okay, so what is it? If it's a constant volume, what would the graph look like? This is a trick question. I wrote that. Think carefully what's constant. If it's constant volume means what? Can volume like change from 1 to 2 to 3 to 4? Can volume change? The answer, of course, is no, right? The volume shouldn't change, meaning B is also not correct. You can't move this way. Cannot. You can't move this way. Also cannot. Oh, sorry, volume, right? Volume. Volume is constant, meaning you also cannot move volume this way. Cannot. Volume just can't change. Volume must be a fixed number. The only graph that shows volume is a fixed number is actually C. Because volume is constantly at a fixed, unchanged volume. The only value for volume is that particular number there. So the only graph that makes sense is actually C, because that's the only one where the volume is unchanged. So you can see, this question is actually not about ideal gases, to be honest. All right, they just wanted to test students whether they know what isochoric means. So today you have learned isobaric, that's same pressure, isochoric, same volume, isothermal, which is same temperature. Okay, so I hope you have learned something from this today. This is the actual ChemO question. All right, so graph C, graph C means you're so tricky, right? So actually the answer is A, because if you look at the 4 options, right, option A is graph C. Graph C is correct. Okay, graph C is correct. Okay, so again, ChemO also must be careful. The A, B, C, D, option A, B, C, D may not be graph A, graph B, graph C, graph D. They can switch the order around. So read carefully. Read carefully. Okay, now ChemO, there are 60 questions. I think you're given 1 hour or so to do it. Please read carefully. The 60 MCQs. Don't just quick finish and get over and done with. Remember, we are not here just to get over and done with. We are here to do our best. Okay, now I promise to do a short revision on what we have done so far. So if you think through, right, set number 1, we started off by talking about separation techniques. How do you separate different mixtures? So that's relevant to what you learned, right? You have learned distillation, fractional distillation, chromatography. You have learned how to use RF values, locating agents in your daily lessons. But set 1, we went on to talk about other applications. What are some advanced applications of filtration? For example, we talked about vacuum Buchner filtration. Chromatography, we talked about radial chromatography, 2-dimensional chromatography. Okay, so that was separating mixtures. Set 2 and set 3 are linked. We talked about atoms. Then we move on to talk about the electronic structure of atoms. Then we talk about ions, ionic bonding. Then we talk about covalent bonding, finally metallic bonding. So we really look at the structure of the materials. Then we move on to set number 4 today, which is about ideal gases. Looking at particles, what are their energies like? How can we describe gases using the ideal gas equation? Bearing in mind that actually real gases may not always be like this. Okay, but the ideal gas is just a good model to continue with. Okay, so really for the 4 sets so far, what we have done really is to look at materials, how to separate mixtures. Mixtures are materials. And we look deeper into the material, the atoms, the ions, the molecules inside. And today we have finally ended off by talking about how these particles have energy and how the particles can be described using an equation. PV equals nRT, the ideal gas equation. Now, why am I ending this session here with a summary? Because from set number 5 onwards, we're going to move on to something that's quite different. We're going to move on to the chemistry of reactions. So next week, set number 5, we will be doing acids and bases. Something you have learned even in lower sec, okay, for the sec 3s. You have learned what acids and alkalis are, for example. So we're going to delve deeper into the reactions. How do acids react and change? How do alkalis react and change? Okay, so next week we'll be doing acids and bases. And the following weeks, we will do more and more reactions. So we are moving on to a different theme. From the structure of materials, we are moving on to the reactions next. So from next week onwards, expect to hear more about chemical changes, chemical reactions. Okay, so that's the end of the session today. I will stop recording now. Thank you.